Let's start with the concept of dead state. Some other names of dead states are waste buckets, Davy John lockers, and rejecting states. When a transition enters in this state, then there is no way to leave with. And once there is no way to leave it, means there is no choice to reach in accept state. Graphically, the dead state is often omitted and assumed for any input that the machine does not have explicit instructions on what to do with. A machine may have multiple dead states, but at most only one dead state is needed per machine. In simple words, check only two conditions. First, if a state has no outgoing transition. Second, that state is not an accept state. I elaborate it later with the proper example. Let us start with the first example of finite automata. Consider the language L defined over sigma a and b for all strings including lambda. The regular expression of this language would be a plus b clean clear. This one is the simplest finite automata. One state that is initial as well as final, because we know it has a special meaning in finite automata, and that is if a state contains both initial and final symbol in it, that machine generates lambda in it. So the first word is lambda generated by this finite automata, and then from transition A we get single A and then stop that machine. If we want to get a single B, then from transition from this edge we can get or retrieve B and then stop that machine. If we want length 2 words from that finite automata, we move our transition, means that edge, 2 times and then stop that machine. We can generate all these words that mention in the set from this finite automata. Lambda, single length 1 words A and B, length 2 words AA, AB, BB, BA, length 3 words and up to so on. This machine is also acceptable for the above mentioned example, all strings including lambda. From state 1 we get lambda. From that transition we can get A or B and stop that machine, and for any combination of A or B or any length word we can generate A or B from that state 2. Means from state 1 we accept lambda, from state 2 we accept A or B or any combinations of A and B. Let us consider another example. Language of strings defined over sigma A and B containing AA. The condition imposed on this machine is it must contain AA. Means this machine not be able to accept lambda. The regular expression of that machine would be A plus B clean clear, AA, A plus B clean clear. If we get lambda from left hand side and right hand side, means from A plus B clean clear, even then that machine would generate AA. This one is the machine for that language. To make your machine more accurate or correct, then my suggestion is to make all the desired tasks first. After that, complete your machine. Condition is we have to accept AA. So we make 3 states and 2 transitions of AA. From that machine we can accept AA. So after 2 A's we make a final state. Now we have to make our machine deterministic. Means we have to complete both A's and B's on each state, as I mentioned in my finite automata video lecture. At state 1, B transition is missing. So we add B transition at state 1. Now both A's and B's are completed at state 1. At state 2 again B transition is missing. So we add it, but if we move this transition towards state 3, then our machine may accept AB and not generate AA, means that transition can demolish our machine requirement. So we move our transition at state 1 towards that direction. Now both A and B's are completed at state 2. Now state 3, both have A and B missing. So we add both transitions on state 3, means after getting AA, we can get any word from state 3. This machine is now deterministic because all states have all the input letters movements. Now consider example number 3. A language of strings of length 2 or more, beginning with and ending in same letter. The condition imposed on this machine is that it must start and end at same letter. The regular expression of this example would be A plus B clean clear A. If we start with A, we have to end our machine with same letter A, and for the same case of B. If we generate lambda from A plus B clean clear, then the machine would be look like this: A and A. Start with A and end it A. If start with B, then end it at B. Next step is to make that finite automata deterministic. At state 1, both transitions are completed. At state 2, A transition is exist but B transition is missing. The only choice to make a transition of B at state 2, because otherwise our condition will be false. Same for the state 3. B transition exists and A transition is missing, so we make a transition of A at state 3. State 4 and 5 both have missing transitions for A and B, so we add them but with the consideration of our imposed condition. If we get B at state 4 and that state is except state, so B transition is not allowed there, so we move that transition towards the state 2, and same for the state 5 for letter A. For transition A and B, we are same at the state of 4 and 5, and that finite automata is the full representation of the example number 3. All those words that start and end in a same letter. Now consider another example of even language. Even means even number of A's and even number of B's. That is the full finite automata for even language. Let's start its building. State 1 have both initial and final symbol or signs, means machine generate lambda, and we know 0 is an even number, means no number of A's and no number of B's. Machine get 2 A's, A, B, A and B, means 2 number of A's and 2 number of B's. If a machine start with B's, then A, then B, then A. Again, this machine fulfills the condition of 2 A's and 2 B's. Now complete that machine, means make it deterministic. Each time this machine generates even number of A's and even number of B's, and all the movement or transition of A's and B's are completed at each state. Let's suppose A, B, B, again B, A and B, means 2 number of A's and 4 number of B's, again even number of A's and even number of B's. It is to be noted that to build an finite automata accepting the language having less number of strings, the tree structure may also help in this regard, and I think that strategy is the best one. Let's consider with the example number 5. This language accepts only 4 words: lambda, b, ab, and bb. At state 1, we have both the sign of initial and final because that language would accept lambda. At state 1, we have 2 childs, A and B, because sigma set have 2 letters A and B. And then further nodes all have 2 childs and up to so on. This language accepts single B, so we make our state 2 with a final state. This language accepts double B also, so we after 2 transitions of B, we made that state final state. This machine accepts A and B, so we make state number 5 as a final state. Now all 4 words are accepted by this finite automata: lambda, single B, double B, A and B. Here in this machine, state number 8 is dead state. As I mentioned at the start of this lecture, because that state has no outgoing transition and also not a finite state. So this state will reject all the words other than lambda, AB, B and double B. This machine is another representation of the language of, for example, number 5, other than tree representation, but in my suggestion, tree representation is the easiest way to draw your machine of finite automata.